So that takes us to the next topic, which is PMFs and distributions. And PMF here stands for probability mass function, which is a way to characterize a probability distribution for discrete random variables. So what are probability mass functions? So as I said, this relates specifically to the discrete case. So in the discrete cases we've already seen, the distribution is defined by essentially the probabilities that we assign to each value. So now we're dealing directly with the value space, each value x in x. Right. So this set of values, basically the probability, right? So this is now our p of x, right? But I'm just going to write p. We're going to forget all about the push forward and all of that. We're just going to say p, and it's defined directly on this value space x. And we're not going to bother talking about measurable sets, at least for the time being. Well, it doesn't matter anyway in the case of discrete, because all subsets, in fact, the whole of the power set is measurable. So in the discrete case, this here, the values of each of these, right, are just numbers. So let's say for xi, it's just pi. These values completely describe the distribution. So once we know all of these values, we know our distribution. So these values, the list of these values, or considering them as a function of x, we call a probability mass function. So here is the definition. The probability mass function, or PMF for short, because probability mass function is a bit of a mouthful, for a discrete random variable, is precisely this function px at x. The probability on the elementary events x for all elementary events in our sample space. We don't. So in terms of the original sample space, I said we were going to ignore it, but I've actually shown it here, I guess, for the sake of completeness. But normally we can just forget about this and just write p of this thing here. The point is, this probability mass function is a function of x, and it's defined as the probability in value space of this elementary event x, a realization of our random variable for each random variable. So ranging over all of the realizations x, we end up generating a function of x, which we call px of x. And that px of x is our probability mass function. Now, from the axioms of probability, what does this mean about px, our probability mass function? So we know that p of x, the probability that we've either defined directly or the push forward, on any set A has to be greater than or equal to 0. So non-negative probabilities. Px of the whole sample space has to be equal to 1. And we have additivity. So Px of A is the sum, in the discrete case, of Px, the sum over Px of all the elementary events in this subset A of our value space. Because, as I explained before, this A will be a union of singleton sets in the discrete case. So, in fact, let me recall those. I explained it before, but let's go through it again. It's always good to remind people of things you tend to forget, including me. So, in the discrete case, whether it's finite or countable. Every event is a disjoint union of singleton sets. So every A can be written like this for all x in A. And that should be hopefully obvious to you. You know, if we have a set like this, 1, 2, 3, 4, 5, let's keep it finite for the sake of argument, for the sake of simplicity, then let's take the subset of this, S equals 1, 4, and 5, right? Well, this is a union of singleton sets of this set. 1 union 4, union 5. So this is always the case. Every subset is a union of singleton sets. And then using additivity, because each of these is disjoint, we get one or the other. We can't have them all at the same time. We get this relationship, which is what I wrote down before. Now, we are literally defining this thing here as Px of x. The value of our function that we're defining, the probability mass function at x. So these axioms then tell us that Px of x is greater than or equal to 0 for all x in our value space, and the sum of Px for all x in our value space is 1. So let's have a look at an example. I went through that a bit quick. So that comes directly from basically this here, right? Because this is a union of all the elementary events in the value space.